Hello everyone, welcome to another live coding. So in this one we're going to do the detecting brain tumors again. And so what we're going to do is we have a data set of images, some with brain tumors and some with not. And we're going to build a classifier to detect which is which. And we'll mostly be using, we'll start with a VGG-based model, pre-trained, which we'll be doing transfer learning on. And then I figured we would try a few other pre-trained models. So we'll try out MobileNet at least and see how that goes. And we also have dropout function working now on the dense components. So we'll give that a try as well and see if we can get some better validation accuracy. All right, but let's jump into it. As usual, this is how the dataset's looking. Or as usual, we go through the dataset first, and this is how the dataset's looking. And we have our CSV file, and we have the images, two different categories. Here are the ones without brain tumor, and here are the ones with. And just looking at them, it doesn't seem too bad to spot which one's which. Some of these have pretty large lumps here and there. So hopefully it wouldn't be too much of a trouble for the model to detect them either. But we'll see. And the CSV itself looks like this, where we have the images listed over here, and then the corresponding label listed over here. Got a question if PerceptiLabs will support sparse matrix. In which scenario do you mean with sparse matrix? Do you mean as input data, or do you mean as a way to store the data inside the model, or as some computational on the data? Anyway, so we have this CSV, and we'll start creating a model. Let me swap over to that screen. So first thing first, we just load the CSV dataset. And we have inputs of the images, and then we have the labeled targets. So we wanted to put out yes or no. And we have automatic recommendations now in. So it'll recognize that this is an image and this is binary. I'm going to swap this over to categorical though. It should work the same. I think the binary currently just gives a single output rather than two, which categorical will. So this will be a little bit more traditional. And everything else looks good, so let's customize it. And for your question, Fast Neuron, on top of my head, you will be able to put in arrays, and those arrays can be sparse matrices. So as that input data, you can put in input data. For computation, I would love to know more about what use case you're thinking. You can hit me up in Slack after this, or in the forum, or by my email, and I can take a closer look at it and see if it's something we will support. All right, so let's start creating the model. Oh, and thank you for the question as well. We love hearing different use cases that people want to use in PerceptiLabs. So hopefully we can support it as best as possible. So the the baseline model I'm going to start with is a simple VGG model. And by surprise, that uses a VGG16. And we're going to keep it not training, and we'll have it load the ImageNet. So very standard here. We also won't include the top. And what this means is that this one is just going to use as a feature extractor. And then we're going to use to create a trainable model here, which uses these features and learns from them. So let's drag out some dense layers. We can start with just 2. And we get an error here because we're trying to output 10 different classes when we only need 2. We'll need to fix that. But let's start with putting this to 128 neurons and a really low activation function. I put it to 128 because I had pretty good success with that before. You can try 512 as well. We might try to bump it up to that. It will make sure that the model is a little bit more complex. It might learn the data better, or it might overfit. We'll find out. And the output we want 2, and we want softmax here. The reason for softmax is very standard to have on the output. It just makes sure that the sum of all outputs equals to 1. So you get a nice output distribution, which is exactly what we want for classification. And then we can start running it. So cross entropy, it's a somewhat smaller data set, so I'm gonna run on batch size 4 instead of 32. And I don't think we need 100 epochs. We can start with 10 and see how that goes. Then we'll run it. Yeah. All right, so it starts running, and I never noticed that there was a label in front of that before, or a text. That should be fine. All right, so this is how it looks like. Let's quickly swap over to gradients, see that they are not 0. If they aren't, or they get very close here. We have our accuracy, which starts off really nice. The validation actually starts off better than the training, which is fantastic. Oh, here it drops really badly. So let's see if it recovers. Anyway, it started really high, and it's not surprising because we are using a pre-trained model in front, so it should already have learned the essentials, and it looks like just 1 epoch is enough to get it in decent accuracy after that. Thank you very much, Phi6. And here we're up at 100% training and 94% validation. Which in many cases are as good as you can ask for a model. But let's see if we can push it even a little bit more. So validation 90% is what we ended at, and training 96. At the very end, I'll show the test view as well. We're getting an update on the test view, so it'll be a little bit easier to see what's happening. But I'll show it off at the end. Alright, so that was BGG. Now let's try MobileNet and see how that one's doing instead. Let me write that down. We had 96.5 for training and validation 90. So let's just swap this one out. And this is all you need to do. And you will have a working model again. And we can run with the same settings. So we'll reproduce exactly how the other one ran. And we'll see how this goes. After this, we can tag on a dropout as well on the dense and see if that improves things, or if, we didn't look at the loss before, we should have looked at the loss, but it didn't seem to overfit at all, which also means we can probably train for a bit longer until it starts overfitting. Just like before, we're looking at the gradients. Gradients is something I default to just because if they explode, something's bad. If they're 0, something's bad. You want them decreasing in a nice manner. These ones are oscillating and jumping around quite a lot, so it might not be that good. And we can see here training is up higher, but validation is a bit lower. And we can see here very clearly in the loss how the training loss is quite a lot better than the validation loss. So most likely it starts overfitting on the mobile net at this point. So let's mobile net, we had 98 and 82. All right, since the mobile net started overfitting, let's try adding some dropout to the dense layer. And what dropout does, dropout is a regularization method. And how it works is it randomly drops neurons out, and this kind of helps the model to not overfit. There are a few different ways to imagine what this does. You can either look at it as it's creating a lot of different models and then averaging them, or you can see it that the important part here is that the different models are smaller than the original model, which means that it's less prone to overfit. It's less complex. It's not gonna hug the data points as tightly as a more complex model, and it may therefore perform a bit better. So let's try that and see what happens. There we go. After this, we can try the VGG again and see if adding or just training it a bit longer will make any good difference. We're also seeing that pretty much all samples we see were spot on with the prediction and ground truth. So the model is already really good. It's as we saw before, it's over 90% accuracy a lot of the time, so there's not too much we can keep improving on. Well, we did bump up the validation a bit, and we did bump up the training a bit, but that it might also be because how it was initialized, rather than adding the dropout. We can see still that we have the validation loss a fair bit higher, and it's going up as well, which is a bad sign. While the training loss keeps going down. So let's try swapping back to the VGG and see if that one performs better with the dropout. And after that, we'll do a quick test with ResNet, which is a much larger model, and see if how that one performs. Let me write this down. So mobile net dropout, I think it was 184. Well, this we saw the last mobile nets dipping down a bit as well, oscillating on the accuracy, which is curious. I'll see. If we wanted to optimize on validation training, we'd probably stop here. But let's see if it keeps that up for the 10 epochs, or if it starts dropping down. And the loss might be more telling here. So this loss looks a lot better. We have the validation loss. The validation loss is oscillating, but it's not going up, which is what you really want to watch out for. Okay, so it starts going up here around 7 to 8 epochs. So we probably would want to stop it around 5 to 6 to get the better model. And the training results look very similar to what we had on the mobile net. So we have 93 and 82. All right, let's try out our ResNet and see how the a little bit larger model's doing. Oh, and I can also quickly show, I think this is in this version. Yeah, we have pre-processing coming in now. So normalizing is already in, so you can normalize your data. But we're also getting random flipping, random cropping, rescaling, so that you don't need to currently you need to make sure that your data set is rescaled or all the same sizes of images before you put it into PerceptiLabs. That pre-processing option is going to be on by default and automatically rescale your data. You can of course turn it off, but that'll make sure that you don't need to worry about that any longer. So let's run this one. This one might take a little bit longer to start. But there we go. Okay, so far is everything looking good. But it's definitely taking a little bit longer to train, it looks like. Now, if I had done this smart, I would have created a new model for each of these, or duplicated the original model for each of these, so that we could compare the training times. But I guess we'll never find out. It's looking between different model versions is something else that's coming out probably late summer around there, where we'll add a version control. So you can see the different versions of your model. You can see how long they took to train, you can see the accuracy and the loss. And you can also swap between the versions. So it's going to be very easy to do exactly what I'm doing now, but without using Notepad and having to write everything down. All right, so this one did not perform as well. We have 89 training and 80 validation. And finally, the last pre-train we haven't tested yet is Inception. So let's give that one a try as the last model. Other things we can do is, of course, increase the number of layers. I'm a little bit hesitant of doing that since we're already starting to overfit a little bit with just these parameters. But maybe adding some nonlinearity would work in our favor. The other thing we can do is, of course, increase the dropout, or we can just reduce the number of neurons in this dense layer with 128. Alright, so these gradients are oscillating and growing. Let's see if they calm down at some point or if they're going to keep exploding. The accuracy, well, we only have 2 data points so far, so I shouldn't say too much yet. Let's take a look at the loss. Training loss going down, validation loss going a little bit up and down. All right. This one did run really stable though. Let's write that down. It has 186. And except for this bump, the loss was okay-ish. All right. So the results we have so far is that VGG baseline is probably the best with training 96 and validation 90. With inception coming pretty close, having 100 training and 86 validation. So let's go back to the VGG, remove the dropout and try adding another layer. So disable that. Actually, we should just do it like this. And let's reduce them all a little bit. So we can maybe have 64 and 32. Something like that. Let's try running that. Hey, you're... Alright, let's take a look at the loss as well. So these gradients look pretty decent. They were oscillating, but they were decreasing. And the loss in general, if it just kept this behavior it has here on the start, it would be perfect. But I'm guessing that maybe the sample size or the dataset size is too small with how complex model we're training on. Yeah, that did not perform that well. Let's go back and just take a 64 dense layer and see how that one performs. Oh, the end results were actually decent, even though the loss went pretty bad. Okay. It did as well as the inception. Alright, so let's try this one. And so this is just a smaller version of the model which worked really well. I think this is the last one we're trying out. Thank you very much, Chris. All right. And also, sneak peek. The next live coding, I'll be looking at building a unit. I got some really cool data for that. And what we'll be doing is segmenting cells. So keep an eye out for that. Hopefully that's going to be pretty cool. All right. Training loss looking decent, validation loss looking unchanging until it's spiked here. And accuracy following the loss, which is very common. Okay. There we have the results. 96 and 86. Not terrible. But turns out that the best model we tried was the actual first one, which looked like this. It had the VGG and then 128 neurons here. But yeah, we iterated on 6, 7 different models. And the next step of this would probably just try changing. The VGG seems to work pretty well. Try changing these dens, maybe a little bit higher dropout could help. And yeah, it seems like this one makes quite a lot of difference in this one, which is not surprising since this one's frozen, this one's very thin. Well, it has more parameters since it's connecting all of these neurons to these ones, but it's not as impactful as this one. But that's gonna be it. Thanks everyone very much for watching, and I hope you all have a great rest of your day. Take care, everyone.